Okay, first we have the inverter. Gates. Or is it ER? I think it's ER. Inverter. The symbol for the inverter is a triangle with a bubble on the output. General conventions on drawing schematics. The input is going to be, the inputs are going to be at the top or the left of the diagram, whereas outputs are going to be to the right or to the bottom of the diagram. So just generally speaking, when you see a diagram, inputs are going to be the left, top, outputs, right or bottom. The bubble indicates that the signal at that point is inverted. It could be on the input or the output of the gate or symbol. In this case, the output is inverted. What that means is, we'll get to a state table here. That is a state table. Some people incorrectly call it a truth table. It is not a truth table. It is a state table. Truth table is for philosophy and math classes. There are more states than true and false, so we'll get into those later on in the semester. But this is the state table for the inverter. If the signal is low coming in, the output is high. If the input is high coming in, the output is low. Pretty simple, pretty straightforward. For logic, for the Digital Logic Lab, low means it's connected to ground. High plus 5 volts, I believe you use for the circuits in the lab. So if the input is connected to ground, the output is 5 volts. If the input is connected to 5 volt positive, the output is ground. This can also be used with binary. Where ground equals 0 and high 5 volts equals 1. But yeah, it's a pretty basic gate, just one input, one output. Pretty straightforward. When we get into Boolean expressions, this is A and A bar or A prime. You have A, the signal A, and the output is either going to be called A bar or A prime, depending on if you are typing it up or writing it out. Doing an A with a bar over it on a computer is challenging at best. So you would do A prime, A apostrophe, to indicate that it is the signal A inverted. All right. Let's see here. I think that about covers the inverter. Oh, I'll go ahead and show you the pinout for the chips that you're going to use. You should learn this in the lab today or Thursday. Well, this week sometime. Your chips that you're going to use have 14 pins. The chip is only about yay long, so less than an inch long. The pins are numbered one. Well, let me do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. So in each package, and that is this package is called a DIP package, dual inline package. You'll see sometimes it referred to as a PDIP, which means plastic in dual inline package, or CDIP, ceramic. But I drew this little notch here because to know the orientation of the chip, you need to know where pin 1 is. And it is on the end with the notch out of it. Some will have a little circle drawn by pin 1, depending on the manufacturer of the device. In the pinout, the arrangement of the gates within the package are like so. So you have 6 inverters in one package. In order for the gates to work, you have to give the chip power. So you have to connect pin 7 to ground and pin 14 to 5 volts. Otherwise, it will not work. I am not remembering the package number at the moment. They'll give you that in the lab. But yeah, this is the way the gates are arranged within the device. This is called, the device, the chip is called a hex inverting buffer. Hex for 6, and the symbol without the bubble is just called a buffer. And with the bubble, it makes it an inverting buffer. So it is called, the package is called a hex inverting buffer. I think that's about all there is for the inverter. Let's see here. Let's go with the, has everybody got this? Pretty much? Yeah? Okay. We'll go with the AND gate next. The symbol for that is a half of an oval where you have 2 inputs and 1 output. And the state table the thing about state tables is they show all possible combinations of inputs and their outputs. So here we have a device that looks at both inputs. If they are both high, then the output is high. Otherwise, the output is going to be low. And if A and B are both high, then it's high. If not, then it's going to be low. So in the Boolean expressions, you'll see A star B or just AB. It is like multiplication and treated like multiplication in regular algebra. Sometimes you'll also see A dot B as well, depending on the documentation you're looking at. If you look at the binary representation of the state table, you can see why it can be used to represent multiplication. 0 times 0 is 0. 0 times 1 is 0. 1 times 0 is 0. 1 times 1 is 1. So in a lot of respects, it resembles the multiplication and operation, and therefore uses the multiplication notation from regular algebra. Now, let me Go ahead and do the pinout for this. The pinout for the quad AND gate package looks like so. So you connect your wires, inputs on 1 and 2, 4 and 5, 10 and 9, and 13 and 12. Again, you have to have, apply power and ground to the chip in order for the gates to work properly. So let's see here. Anything else about the AND gate? Well, honestly, that looks to be about it. It's a fairly simple gate. It performs the multiplication operation with binary inputs. It will be used when we get into hardware multipliers for just this purpose. This is in a few weeks. But yeah, pretty straightforward on that. The OR gate is the last gate of the three basic. The OR gate is a little bit of a funny symbol. It's kind of a stylized arrow. It's curved on the input side and kind of an arrow pointing toward the output. Again, the operation is an OR, so if either input is high, then the output is high. If they're both low, then the output is low. So in binary, it looks like this. The Boolean expression representation is a plus. And it kind of does resemble the the addition operation in regular algebra. 0 plus 1 is 1. Well, 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. The only difference is the 1 plus 1 is 1. Throws it off a little bit there, but it is the addition operation. It is represented by the plus sign. Uh, and the pinout and quad OR gate. The pinout is similar to the AND gate, with the same inputs and outputs, just a different gate in the middle. But with these three gates, you can do realize any Boolean function. This is all Boolean logic. Boolean meaning high or low, 1 or 0. I want to say it was invented or first characterized by a gentleman by the name of Boole, George Boole, I think. I have to look that one up. But these form the basic elements of all logic circuits within computers. They're all based off of these three basic gates. There are other gates that are also used for increased efficiency and that sort of thing, which we'll get into a later time, but these are the ones that you're going to be using in the digital logic lab. Like I said, going through this quickly because I want you guys to be prepared for the lab. With general circuit assembly, you can have multiple gates working together. For example, a 3-input AND gate can be created by stringing the output from one AND gate to the next to the input of the next AND gate. Inputs can come from the output of another gate. What you cannot do is link two outputs together. So you to do a 4-input, you can't go you can't do that. This is a big no-no. The reason being is if this this AND gate is high and this one's low, then you have a circuit from high to low. That's called a short circuit. And things start smoking. And we all know smoking is bad for you. especially in the lab. So you do not link two outputs together. To do a 4-input AND gate, you would have the outputs of the two input AND gates into an output AND gate to bring the inputs together. So the state table for this, like I said, you have to have every possible input. It would be hello, and so on. You have to have every combination. There would be, in this case, 16 possible input combinations, because your combinations equals 2 to the n combos. N is number of inputs. So how many possible combinations would be there for this, of inputs for this, the 3-input AND gate? No, not 3. 2 to the 3rd power, not 2 times 3. 8, yeah. So there would be 8 possible combinations for the inputs here. And in both of these cases, the 3-input and the 4-input AND gate, it's only high if all the inputs are high, otherwise it's going to be low. If you actually have a 4-input AND gate, the symbol would be like so. Likewise, a 3-input would be like this. So you can have larger inputs depending on what gates you have available to you. And these configurations also work for the OR gate, the 3-input OR gate is like so, and the 4-input OR gate Now what you sometimes see with the OR gate is the back line extended a little bit to allow for more space between the input lines, and then and the output for that would be high if any of the inputs is high, and low if they're all low. So an example of a little bit more let's do it on this one. This Boolean Boolean function is an OR gate feeding into one input of an AND gate, ANDed with C. So let's look at how you would construct the state table for that. A, B, C. I'm going to use binary because it's easier to write. That's 8, right? Yep. All the possible combinations. And your output, you work from left to right. A or B is, you can write this out in stages. You do A plus B. And then A plus B and C. So A plus B, 0, 0, 1, 1, 1, 1, 1, 1. You see where I got that? The state table for A plus B, A or B, 0 or 0 is 0, 0 or 0 is 0, 0 or 1 is 1. Again, 1, 0, 1. Again, 1 and 1, 1 or 1, 1 again, and same thing again. Now we'll take this column and add it with and multiply it with the third column. So you AND these two columns together. So 0, 0, 0, 1, 0, 1, 0, 1. So you break it down by and construct the state table by the gate and the individual functions that the gates produce. It's not right anymore. So that would be the state table for this circuit. So now say you have a expression and you want to create a circuit from that. Say you have A prime or B and C. What's the order of operations for algebra? What comes first? Parentheses. What's in the parentheses? So you have B and C. In Boolean expressions, you take care of inversions before you do addition or and. So you'd have an inverter on A, and then you would OR the inverted A with the ANDed B and C. And then the truth table, or the state table, I teach math where I use truth tables, so I get a little muddled sometimes. So you would do A prime, which is the inversion of A, which would be 1, 1, 1, 1, 0, 0, 0, 0. Then you would do the B and C. B and C would be all zeros except for, or no, except for here. So 0, 0, 0, 1, 0, 0, 0, 1. Oh, I didn't. And then you would take the OR of A prime or B and C, which would be 1, 1, 1, 1, 1. So you would OR these two columns to get your final expression. So I want to say that should get you through, that content should get you through the next couple of weeks of Digital Logic Lab. How to write, how to draw your schematic diagrams, and the notation for the logic functions, how to create a state table, how to create a state table from an expression, how to create a state table from a schematic. We'll get into how do you make a schematic from a expression in later well, no, you can just do the we did the schematic from the expression. We did all three combinations. But any questions about all this? Like I said, I know I went through it a little fast. But any questions about how to do this sort of thing? Need some more examples? Yeah.
So, alright, so I get like the little tips, like the whole first part where we're talking about the inverter, like the OR gate is like the base, I guess.
Mm-hmm.
It's when you get to this part, like with the long diagrams, like I got a little bit lost. So you're going from like that little math equation to, so I know like because like one of them was an OR, and then you're just like Robert lost it. Get like to the combination.
Of different gates together?
Yeah.
Oh, okay. Well, you in this situation, you have A inverted. So you have that, so that's right here. So this is A invert, or A not A, however you want to express it. Then you have the the contents of the parentheses, which is an and. So that's here, B and C. And then you OR them together. So this is here, and this is here. So A prime or B and C. Yes. Yeah.
My question was, so you can only have one output, but you can have multiple inputs.
You can have multiple inputs. Later on, we'll get into multiple outputs as well. But for the time being, like I said, I was just preparing you for the lab. The first 5 or 6 labs, you're only going to have one output. Yeah. Just real quickly, just as an example, that is what's called a half adder. It adds the 2 binary numbers together, where the output is the sum and the carry. So the state table would be this symbol I haven't introduced you yet to. It's called the exclusive OR. But it has a output of this, and the carry is simple and. So your sum is going to be either if A and B are 0, your sum is going to be 0, and your carry is going to be 0. If A and B are 1, your sum is going to be 1, because 0 plus 1 is 1. No carry, because the it's less than 2. And then likewise with A and B, if A and B are 1 and 0, sum is again 1, carry is 0. If A and B are both 1, binary math, right? So you need a 1 to carry the 1, and your sum will be 0. So actually, I should have been putting this. Whoops. See, this is an example of having 2 outputs. Like I said, we'll get into this. We'll go into this in more detail later, after we introduce the exclusive OR gate and other things.
Yeah, I was thinking we could have outputs.
No, if you link 2 outputs together. Yeah, you can't link 2 outputs together. The outputs of 2 gates. Yeah, see, the outputs of these 2 gates do not touch. So that's okay. See, these 2 gates, the outputs are separate. They're separate wires. A little schematic notation as well. If you have an intersection of lines, if they connect, you put a dot over it. If they don't connect, you just cross the lines. Yeah. Okay.
So in that one above, the one you just did,
Mm-hmm.
able to be connected right there because of the converter, or is that not considered an output?
Yeah, this is an output, but it's not connected. It's only connected to an input of the next gate.
Oh. Okay.
Yeah, you can go from a output to an input all you like, but it's just a matter of having two connected outputs is a no-no.
You can't just like if that gate was
No, you would have to put the OR gate or some other mechanism to bring them together. So
they pull into the same gate. When they pull into the same gate, they give
in this case, it gives the OR function is between these 2. The output of this gate and the output of this gate is ORed together. This could be an AND gate and have a different function, but
as long as they bridge together before they make an output.
yes,
The output.
that's right. Yeah. So there is one special exception that I'll get to very much later in the semester, but for the most part, you can't link outputs. And you can have as many outputs as you want, depending on what function you're trying to realize.
Don't get some water mixes all this up. That's why I think
Yes.
scrambled all this.
Yep. Water is typically a conductor. So it's like putting a pile of copper or another conductor on your circuit. Things start getting screwy and things short circuit, start smoking. I've even seen small explosions in the lab upstairs. Yeah, a short circuit can generate a lot of heat, enough to melt metal. That's what a arc welder does in a controlled fashion. But Yeah, we don't want that in the lab. Yeah. Any other questions? Clarity? Examples? Yeah. Well, I went through that faster than I anticipated. But good luck in the lab. Have fun. Get to experiment around with different circuits. I believe it's still the case for those of you that are computer science majors. It's the only hardware class that you're going to have. So, if you enjoy it, you might want to change over to computer engineering. I don't know. That's up to you. But yeah. Anyway, have a good day. See you on Thursday.